Look up at the night sky. Every star, every planet, every galaxy you can see, it's all made of the same stuff we are. The atoms and molecules that make up you, me, and everything we know. But what if I'd told you that all of that, everything you've ever seen, is just a tiny, tiny fraction of the universe? The truth is, over 85% of all the matter in the cosmos is something we can't see, touch, or even measure directly. It's called dark matter, and it is the universe's greatest mystery. So what exactly is it? And more importantly, what does what we don't know about it tell us about the future of physics? Our story starts almost a century ago with a brilliant and eccentric astronomer named Fritz Zwicky. Zwicky, a Swiss-American astrophysicist, was known for his colorful personality and groundbreaking, if sometimes overlooked, theories. In the 1930s, he was studying the Coma Cluster, a massive group of galaxies. He measured the velocities of galaxies within the cluster and discovered they were moving so fast that the cluster's visible mass was nowhere near enough to hold them together gravitationally. He famously coined the term dunkle materia, or dark matter, to describe this unseen mass. But his radical idea was largely dismissed by the scientific community at the time. For decades, his idea was a fringe theory. But in the 1970s, another pioneering astronomer, Vera Rubin, found a similar problem on a galactic scale. Rubin, a meticulous observer, was studying the rotation curves of spiral galaxies. She expected to see stars on the outer edges of the galaxies orbiting more slowly, just as planets further from the sun in our own solar system move at a slower pace. But instead, she found that the stars on the outskirts were orbiting just as quickly as those in the galactic center. This defied the laws of classical physics. Vera Rubin's detailed and extensive data provided compelling evidence that Zwicky's invisible matter was real and ubiquitous, forming massive halos around individual galaxies. And it gets even cooler. Dark matter's gravity is so powerful it can bend light. This phenomenon, predicted by Albert Einstein, is called gravitational lensing. The gravity of a galaxy cluster or a dark matter halo acts like a giant magnifying glass, distorting the images of the galaxies behind it. By measuring this distortion, we can actually map out where the dark matter is, even though we can't see it. This gives us concrete proof that it's there. A perfect example is the bullet cluster, where we can see the visible matter of two colliding galaxy clusters separating from the dark matter, providing some of the strongest evidence to date. Okay, so we know it's there, and we know what it does. But the big question remains, what is it? For decades, the leading theory was that dark matter is made of weakly interacting massive particles, or WIMPs. These would be new, massive particles that formed in the early universe and only interact through gravity and a very weak force. This theory is compelling because it arises naturally from extensions of the standard model of particle physics, our best theory for how particles work. To find them, scientists have built massive detectors a mile underground to shield them from cosmic rays. One of the most advanced detectors is the Lux Zeppelin experiment in South Dakota. The detector is a massive tank of liquid xenon designed to be so sensitive that if a WIMP ever passes through and strikes a xenon nucleus, it would cause a tiny flash of light and ionization. The LZ experiment has set new world records for sensitivity, but so far, nothing. The WIMP is still hiding. This lack of discovery is fascinating because it forces us to consider alternatives. What if dark matter doesn't exist at all? This is the core idea of modified Newtonian dynamics, or MOND. MOND proposes that our understanding of gravity is just wrong on cosmic scales. It suggests that gravity is stronger than we think at very low accelerations, which would explain galaxy rotation without the need for invisible matter. While MOND works for individual galaxies, it fails to explain the behavior of galaxy clusters, making it a tough sell for most scientists. Another exciting possibility is that dark matter could be primordial black holes that formed right after the Big Bang. These black holes, which could be the size of an asteroid or even a mountain, would have formed from extreme density fluctuations in the universe's first moments. They would be incredibly difficult to detect, making them a very plausible candidate. What we don't know about dark matter has massive implications for our entire understanding of the cosmos. Our current standard model of the universe, the Lambda CDEM, relies heavily on both dark matter and dark energy to explain everything we see. The Lambda CDEM successfully describes everything from the cosmic microwave background to the formation of galaxies and clusters. It's an incredibly successful model, but if a definitive answer about dark matter's true nature or lack thereof is found, it could either confirm this model with the discovery of a new particle or force us to rewrite our fundamental laws of physics. The search is not just for an invisible substance. It's a quest to understand if our most cherished theories about gravity and the universe's structure are correct. The hunt for dark matter is one of the most exciting frontiers in science today. It's a journey into the unknown that challenges us to think bigger and push the boundaries of technology. The fact that the universe is holding a secret this big is a humbling and thrilling realization. It reminds us that there's still so much left to discover. Or as our old friend Socrates would say, the only true wisdom is in knowing you know nothing.